I'm going to talk to you about, well, this is going to be the final chapter in my PhD thesis. It's based on a paper called Impossibility of Quantum Virtual Black Box Obfuscation of Classical Circuits. And if you have asked me over the past, well, probably maybe even 4 years, Yfke, what are you working on right now? You may have heard me mention the word obfuscation. And actually, it was something that I had a lot of hope of constructing. But as you can tell from the title, it starts with impossibility. So we didn't manage to construct it, but I guess it's a small victory then to be able to show that it's actually impossible. Because a lot of the time, if you don't manage to construct something, then, well, you're kind of stuck in the middle. And this result, it came, or the idea came into our heads when Gorian, Yfke, myself, and Chris, the authors of this paper, were all in Berkeley together before everybody had to fly back home. Okay. So for today, the outline is I'm going to start a little bit from the basics. I will define what is this obfuscation, especially what's this variant that I just called virtual black box. I will discuss the proof idea behind a known result, a classical impossibility result, and then our new result extends this into the quantum realm. So showing that even with quantum techniques, this cryptographic thing is also impossible. And then towards the end, I will put it into a little bit of context of some previous works, which will already appear earlier in the talk, some concurrent work actually that happened at the same time, and also some open questions that may happen in the future. And also I want to mention, just interrupt me if something is unclear. I think I have enough time to talk about everything, and otherwise there's things that can be skipped. So if I'm going too fast or too slow, just say so. Let's start with a little bit of an informal definition. So the obfuscation of a program, so this is a very simple program that prints hello world. The obfuscation of that program is itself another program. For example, this string of brackets and ones and exclamation points that has the same input-output behavior, but is in some sense less intelligible. So this example that I'm giving here, it's some JavaScript program, and if you run it in a JavaScript compiler, I guess, or interpreter, I don't know, it will also output hello world. But if you're just looking at this code, then that's, well, I wouldn't be able to tell. So an obfuscation is essentially another...
How did you make it, Yfke?
The attribution is at the very bottom. I went to Stack Overflow.
Okay.
Someone else. So I think this is actually also a little bit of a hobby for some people. Try, like maybe there's even some contests for sort of making the best obfuscated programs.
Cool.
According to some measures of best. Although I have to mention that this is maybe not the mathematical this wouldn't really fulfill the mathematical definition of obfuscation that we will see on the next slide, but this is kind of just to give you an idea. From my point of view, it's very hard from this random string of characters to tell what this program is doing. But that's not to say that the only object that an obfuscation can be is itself another program. It can also be some other object, maybe an image. So this image on the right, it is itself also kind of a program. It's written in the programming language Pete, which I guess you can guess where the name comes from. I'm not sure if it prints hello world, but it does something. Let's pretend that it prints hello world. And also from this thing, unless you're able to read this programming language, it's kind of hard to tell what this will do if you run it. And also maybe looking at a bit ahead of ourselves, why can't we have a quantum state that somehow, if you follow the right instructions, perform the right measurements on it, sort of run it in your own compiler interpreter, would have this same behavior of printing hello world. So informally, this is what an obfuscation is. It makes, it hides the structure of your program or your circuit, but it keeps the input-output behavior intact. And in this talk, I'm not going to view things as programs in programming language per se, but I'm just going to think about circuits. So we always talk about, we want to obfuscate some circuits or some class of circuits. Okay, so a little bit more formally now, what is an obfuscation? I'm going to consider the definition of virtual black box obfuscation, which is kind of the strongest definition that's out there. And we talk about an obfuscator O, so that's like some procedure that takes as input a circuit and produces an obfuscation. And it always works with respect to some circuit family F. And it has to satisfy three properties. The first one is that whatever it outputs, well, it shouldn't be too big. So it should only be polynomial in the original circuit size to preserve some efficiency. This is what we call polynomial expansion. The second property, called functional equivalence, we want that this obfuscation is itself perhaps a circuit that's equivalent to the original circuit. So we want to preserve that input-output behavior. I'll slightly relax this second point later for the cases where it's not a circuit. But the third point is actually the most interesting one. And that's called the virtual black box or VBB property. And informally what it says is it says that you shouldn't be able to learn anything from this O of C, this obfuscation object, that you wouldn't already be able to learn from oracle access to the functionality. So I'll just walk you through this picture and definition a little bit. So for every adversary, A, there should exist some kind of simulator that for all the circuits can produce the same output distribution as the adversary could have produced. So the adversary gets the obfuscation, can look at it, can run it, whatever. And the simulator only gets oracle access to the functionality C. And it also gets, as a technicality, gets as input the length of C. So that's this 1 to the power size of C. And using only that information, the simulator should be able to produce the same input out or the same output distribution as a single bit. So maybe just to kind of zoom in a little bit on this. Oh, yeah, one more slight generalization. I mentioned on the previous slide that an obfuscation is not necessarily a circuit itself. It can also be some kind of other object like this image. So if you want to generalize for that case as well, we add to our obfuscator object another algorithm, the interpreter algorithm. That's this J, I guess. And our functional equivalence then just means that if you run your interpreter on your obfuscation and some input X, then the output should be the circuit applied to X. And in some cases, you want exact functional equivalence, but if we're talking about quantum obfuscation, we often only require, and now this second point, only to hold with high probability, for example. So there's sometimes some kind of error allowed, but those are some details. I want to zoom in on this third point a little bit just to give you some intuition about kind of what it means. So we have these two cases. We have the adversary that gets the obfuscation object, and we have a simulator that only gets input-output access, oracle access. And what is the difference between these things? Well, it really depends on your circuit family. But this adversary, it holds this object. Let's think about this obfuscation, this O of C as a circuit itself. You can break it into pieces. You can look how many gates does it have, which gates does it have. You can compute on it, like maybe change it around a little bit. So if you're thinking about this Pete program, you can see what happens if I turn that blue area into a red area. What happens if I run my interpreter on the image upside down? So you have sort of some kind of object that you can manipulate. And the simulator, on the other hand, only has this input-output behavior. It can query an X and it can get a circuit, or the output C of X can get it back. And as we will see later on in this talk, that's also, this difference is also what the impossibility proof is going to leverage. So we're going to construct some kind of circuit class where really seeing some description of the circuit or some object of that represents the circuit really gives you a lot more power than just having the input-output.
May I ask, Yfke, what exactly do you mean with a simulator?
So,
sorry to throw you off.
I don't know what happened there. So what do I mean with a simulator? That's a good question. A simulator, it's nothing more than another algorithm. So in cryptography, we often use this adversary simulator kind of paradigm to say, okay, a simulator is just an algorithm that should be able to do the same thing that the adversary did, or it should be able to make it look to the outside world as if they're doing the same thing. So in this definition that we had before, we required that the simulator had the same input-output or the same output distribution as the adversary. So from an outsider's perspective, it looks like it's actually doing the same thing, but it's not, right? Because it doesn't have the same obfuscation object and it's using this oracle. But sort of mathematically, it's just an algorithm. And we usually require that if the algorithm A has polynomial runtime, then so should the simulator S. But other than that, there's not really any restrictions.
So is the point, Yfke, that the simulator, I mean, ideally you want that the simulator can get the same information out as the adversary, but the simulator only can have input-output relations and nothing more.
Yeah. So that's correct. So by requiring that, essentially what you're doing is you're putting restrictions on what this O of C object can reveal, right? Because if everything that it could reveal, well, you should also be able to learn just from this input-output behavior.
And if it was a good obfuscation.
Yeah, if it was a good obfuscation, yeah.
And can you put back again this third point? Because I had trouble parsing it, but that should be much easier now.
I think I can, but then I have to click a few times. Oh, yeah. Yes, this one, right?
Yeah. Oh yeah. Oh yeah. And this adversary is trying to determine some property of C.
Yeah. And this is for any adversary. So any adversary that I mean, it just outputs a single bit, but maybe it tries to output some bits that determine some property of the circuit.
That's how to read it.
And whatever it could learn just from O of C, the simulator should also be able to learn just from interacting. So in particular, some circuits, if you have certain circuit families, because this is always with respect to this family F, right? So it should hold for all circuits in the family. If you have a family of learnable circuits, which are defined by you can learn the description of the circuit just from interacting with it a polynomial number of times, just from running it, well then it's allowed that the adversary would be able to learn the full description of C from the obfuscation, because the simulator would be able to do it too. But for example, we will see later on in this talk, we will see a family of point functions, and a point function, it's 0 everywhere, but it's 1 at a single random point. Well, a good obfuscation for that, you shouldn't be able to learn which point it is non-zero at, because the simulator with only oracle access will have a very hard time learning that point, right? It can just query random x's and then hope that it will hit that single point, but the probability that it does so is very small. So from that, you would say, okay, then the obfuscation should also not reveal this information.
Mm-hmm.
Now I have to go to where I was. So this I kind of already said. So what is the difference? Well, sometimes the difference is really nothing. So an adversary in a simulator can do the same thing in the case of these learnable functions. And in some cases, the difference is going to be a lot. And that's what we're going to leverage in the impossibility proof later on. So this is also a good point to ask more questions if the definition is still kind of unclear. If not, then I will move on. So Before I tell you that this is impossible to achieve, I'm going to tell you why we want to achieve it, because then you will be more disappointed that it's impossible. Well, the first sort of very obvious application is for proprietary software. So if you can obfuscate your software program, then, well, you can distribute it to the world, but you don't have to give away your source code. So people can run it, but they cannot tell how it works. Of course, this is something different than copy protection, so they can still illegally copy it and distribute it to each other. But if you have some kind of very secret algorithm, then you can sell it without selling the secret. But the reason that in cryptography this obfuscation has gotten so much attention is more about theoretical applications. So it's kind of a big hammer that we can use on many things. If an obfuscator exists for the family of all classical circuits, or all polynomial size classical circuits, I should say, then we can do lots of things. So for example, we can build public key encryption from private key encryption. We can build homomorphic encryption from the public key encryption, which we could have built from the private key encryption. In some cases, we can implement random oracles, so we can move from a random oracle model to a standard model. And well, there's many more applications, and homomorphic encryption itself has many applications. So it's really like, if you have this, then you can make many things that we would like to have in cryptography. But alas, if the obfuscation object, this OFC itself, is classical, then this is not possible. And this was shown in 2001 already, and I'll show you the argument for that. But then there's this hope, well, what if we allow this obfuscation to be a quantum state? And this is something that for a few years people were really trying. I even talked to someone who had some candidate construction for it, and was trying to prove that that was working. But alas, this hope will also crumble, or partially crumble. And that's what I'm going to talk about next. So I'll first show you the classical impossibility result, because our proof, the quantum one, is really similar to that. So it's essentially, we're using the same proof structure, but we are running into some extra hurdles that we have to get around. And the idea of the classical impossibility result, this was shown in 2001, where we say the class of classical circuits cannot be obfuscated into circuits, but you can generalize this to say into classical objects in general. And it's based on the following idea. So the idea is to construct a circuit family that will become unobfuscatable. So we construct a circuit family with a corresponding adversary of the following structure. So it just contains of two types of circuits, C and Z. I will later define what they look like, but they're parameterized by some alpha and beta, both of them. So it consists of, well, 2 times 2 to the n circuits, and n is just some kind of security parameter. And we want the following to hold. We want that if the adversary is given an obfuscation of this C circuit, it will almost always output 1. And if it's given an obfuscation of a Z circuit, it will almost always output 0. So the adversary can tell the difference whether he got a C or a Z. That's the goal that we want. And at the same time, we want that if we give a simulator, so this, for any simulator, if we give it an oracle access to C or Z, then it will always, like, it cannot tell the difference between those two. So whatever simulator we have, and whatever output distribution the simulator has, it will be the same for this top simulator or this bottom simulator. Right, so our goal is to construct a family F of circuits with this property, that an adversary can tell the difference, but the simulator cannot. And then this would make obfuscating this class of circuits impossible, because if we would be able to obfuscate, then that would say, well, for this adversary, there exists a simulator such that on the top circuit, the C circuit, the input-output behavior, or the output distribution is the same. And on the bottom circuit, for the Z circuit, the output distribution of A and S is the same. And then if you follow these equation signs, then you would get to 0 equals 1. And there's always like approximately equal signs because there's always some kind of small error, but still this error is small enough that you would get to a contradiction. Okay, so that's the structure of the proof that they have. They construct this circuit family, these C's and Z's, which I haven't specified yet, for which the adversary can tell the difference, but the simulator cannot, and that would lead to a contradiction. Any questions about this proof idea? If not, they can also come later. Okay, so now I will tell you what these circuits C and Z actually look like. I'll start with defining the C circuit, so the one in which the adversary is going to output 1. And the circuit, it will consist of sort of 3 cases, and these numbers 1, 2, and 3, they're arbitrary. You can just think of them as, I don't know, 3 circuits in one somehow. If the first is kind of a choice bit or trit. And I'm going to ignore the fact that the inputs are not necessarily of the same length, but you can imagine that if you pad them, that it all fulfills sort of nice circuit constraints. And the first part of the circuit, it's going to be a point function. This I already mentioned. It's 0 everywhere except at the point alpha. And at that point, it will output beta. So if you input 1, alpha into the circuit, you would get beta out. And 1, anything else, you just get 0 out. And on the second option, you don't need to give it an input, but it will just always return some fixed ciphertext for alpha, so an encryption of alpha together with a public key. And it's important that this encryption has a specific property called homomorphic, so it's homomorphic encryption. And what that means is if you have a ciphertext and only the public information, then you can go from the ciphertext of, for example, any value y, you can go from that ciphertext to a ciphertext for some function evaluated on y, for any choice of function. So if I have an encryption of alpha and I want to, I don't know, multiply it by 2, then I can do that if the encryption is homomorphic and I have the public key. And I can get an encryption of 2 times alpha. And that's an important property that we will use later, the fact that this encryption is homomorphic. And the last kind of branch of this circuit, it will do the following. So you give it some kind of input X. The circuit will decrypt that input using the decryption function that corresponds to this homomorphic encryption. And if it decrypts to a beta, then it will output 1. And if it decrypts to anything else, or if the decryption fails or whatever, it will just output 0. And this, for those of you who know this type of function, this is called a compute and compare function. So it computes some function on the input, in this case, the decryption function, and it compares it with some value, in this case, beta. Okay, so I will keep this circuit on the slide because it's quite a lot to remember. But it's just some kind of circuit. It has 3 branches, so to say, a point function, something that statically returns some ciphertext, some encryption of alpha, and something that checks whether something decrypts to beta.
Yfke, can I ask something?
Yeah, of course.
So the secret key for this encryption scheme, is that sort of considered fixed, or how is that chosen?
Yeah, so it's kind of, for every circuit, C alpha beta, you actually draw the circuit from some kind of distribution. I didn't quite specify those details here, but you draw it from a distribution. So you fix the secret key and the public key. And even this encryption of alpha, it's fixed. So every time you input 2, you will get the same ciphertext. So it's not a newly random ciphertext every time.
Okay, yeah, thanks.
And fortunately, the definition of this second type of circuit, so remember our family consists of 2 types of circuits, C and Z. It's almost the same. Phew, we don't have to go through another long definition. except for the first line. So in the first line, this Z circuit is always 0. So that's why where the name Z comes from, it's like the 0 function. So it still has this second line and the third line, but on the first line, it just whatever you give it, even if you give it alpha, it outputs 0. And what's maybe interesting to observe here is that in the Z circuit, the connection between alpha and beta is completely gone. So the original circuit had some kind of connection between alpha and beta. When if you pick alpha randomly and beta randomly, your C alpha beta had some kind of connection on the first line, and in the Z circuit it's really gone. You just get a ciphertext for a random alpha, and you have this last line, this compute and compare line for a random beta. So there's no connection between the two anymore. And now let's say the following. You're given an obfuscation of either C alpha beta or Z alpha beta for a value of alpha beta that you don't know. So essentially you're given a random member of this family. Can you tell which of the two categories your circuit falls into? So whether you got something C or Z? Well, if you only have oracle access, so if you really think of this obfuscation definition as being equivalent to the simulator with oracle access, then no. I mean, this is something you would have to prove formally, but you can kind of see it. If you want to tell the difference between these two circuits, well, you have to query an input on which it acts differently, right? So essentially you would have to query this first line, 1, alpha. So you'd have to know alpha or guess it, but you only have an encryption of it. So informally, you can already see that this is going to be very hard. You're going to succeed with very small probability. But if you have an obfuscation that is a circuit.
And we assume beta is not 0, I guess.
Yes, that's true. Yeah.
Otherwise, I mean, still cannot.
Otherwise, it's going, yeah. That's true. Yeah, beta is not 0, and it's sort of randomized over all the rest. There are a few of these small details that I'm kind of skipping over, but if they confuse you, please just ask. But if you have an obfuscation that is itself a circuit, so you're giving this O of C or O of Z, and you have this object in your hand, then actually you can tell the difference. And I'll show you how you can do that on the next slide. But this is the contradiction that I was mentioning earlier, right? That you have an adversary that if he holds an obfuscation, he can tell the difference, but the simulator cannot. So how do you tell this difference between these two, or an obfuscation of these two circuits? So, okay, you're given an obfuscation, and we're just assuming for simplicity that that obfuscation is itself a circuit. So, and we'll call that circuit D. So D could be that Pete program or a random string of JavaScript, if you think about it. First step you're going to do is you're going to run it on input 2. So you're just going to grab this ciphertext for alpha, and you're also going to get a public key, but okay. That's their first step. Independent of whether you've gotten a C or a Z circuit, you will always get an encryption of alpha there. And then the second step, that's kind of the complicated one. You're going to evaluate D on the first line, but you're going to do it homomorphically. So you cannot, what you would like to do is you would like to run C of 1, alpha, but you don't have alpha, you only have an encryption of alpha. So what this means homomorphically evaluating it is you're going to run it on an encryption of 1 instead of 1, and the encryption of alpha that you just requested. And because this encryption was homomorphic, you can essentially run any circuit on it, so in particular the circuit D, and what you would get out is, I'll talk about that side point in a minute. What you will get out is an encryption of beta, in the case that you got the C circuit, or an encryption of 0 in the case that you got the Z circuit. And you can think about that for a little bit, but for those that are a bit more familiar with this homomorphic encryption, I'll give a side note now. The original proof was actually slightly different. It contained a 4th option for homomorphic evaluation, where they decrypted, applied some gate, and then encrypt it again. So you'd have to run this circuit D gate by gate. And the reason for that was, well, they didn't have homomorphic encryption in 2001. And also you can then show this impossibility result without having to assume the computational assumptions that are necessary for homomorphic encryption. So I chose to present it in this way because it's closer to the proof that we will see later, but that's kind of a side note for the cryptographers among us, but you don't need to remember that part. The important thing is that now, after the second step, you will have, again, still just an encryption, but depending on which type of circuit you got, it will be encrypting a different value. And now maybe you can already guess what the last step will be. You're going to run it through this last line. Your circuit is, again, an obfuscation of either C of Z, but in both cases, it will test whether you're in the third line, whether your input is a ciphertext for B, or for beta, in which case it will output 1, or a ciphertext for something else, in which case it would output 0. So Harry's comment here is fairly relevant, that of course this doesn't work if beta is 0, but for all other cases, you will get a distinction. And then what you would do is just output 1 or 0, depending on what you got from that last line.
So can I ask a quick question?
Sure.
So you're assuming that you have access to this encrypting circuit?
Well, I assume that in the first line, you queried this second option, and there you get a public key. With a public key, you can encrypt.
Oh, I see. Okay.
So essentially, you can do the encryption yourself. And you're right, because that's necessary to kind of compute this encryption of 1. And also during the evaluation, you need the public key again.
Perfect, thanks.
So that's the gist of the proof. We have shown that there is a circuit family consisting of these C's and Z's that and some adversarial algorithm. So that's this algorithm that's currently on the slide that can have different output distribution depending on whether it got a C or a Z. But I argued earlier that no simulator can tell the difference between these two types of circuits. And then we can conclude that for this family of circuits, it's impossible to obfuscate them. And that also because this family of circuits is a family of efficient classical circuits, that implies that the bigger family of polynomial sized classical circuits is also impossible to obfuscate in general.
Can I ask a question, Yfke?
Yeah.
Because I remember when I saw this result the first time, that it was sort of an unconditional result, right? I mean, in your proof, you're assuming that you cannot decrypt this encryption of alpha. But I remember they had a proof that somehow said either you can or you can't, or something like that. Is that, am I remembering correctly?
Of course, the kind of extra assumption that I introduced by using this homomorphic encryption, they don't need it, but they do need, maybe not for all of the versions of the result. They have several versions of the result depending on whether the obfuscator is efficient or not. But for the sort of the standard version of the result, they assume one-way functions existing. And
oh yeah, then it was like
can,
and either that exists or it doesn't exist. And in both cases, they showed obfuscation was not possible. Was it something like that? I don't want to hold you up, but
no, it's not exactly that. If I remember correctly, they show that efficient obfuscators. So if this O algorithm that takes a circuit and produces an obfuscation, that is impossible unconditionally. But even inefficient obfuscators are also impossible if you assume one-way functions. I think that's the version of the result, but I'm not 100% sure. I can look it up after if you're interested.
And then another thing I had when I saw that was that this shows like it's a counterexample to some function that you cannot do, but how damaging is that for functions that we are actually interested in?
That's also still kind of open, I think. So some classes of functions, there are obfuscators for it, even black box obfuscators, So for example, this class of compute and compare, so compute a given function and then compare it to some sufficiently random secret value, that class of functions we can obfuscate, and that's already a pretty interesting class of functions, but still fairly basic. But that's fairly recent, I think 2017, that they found an obfuscator for that. But yeah, you do make an important point that it rules out a single obfuscator for all classical circuits or for this kind of contrived family, but maybe there are interesting families of circuits that are still obfuscatable. That's kind of, yeah, who knows.
Thanks.
Okay, so now let's move on to some quantum finally. So the question that was asked around the quantum crypto community was, well, this rules out the fact that the obfuscation should be a circuit, but what about obfuscating classical circuits into quantum states, right? Because quantum states have this nice kind of hiding of information property. So maybe we can actually sort of put the functionality of a circuit into a quantum state, and you can interact with it in some way to get the functionality, but you cannot learn the full implementation of the circuit. So that was kind of a promising direction, and the question was first posed on paper by Alagic and Pfefferman in 2016. And in this talk, I will show that this is unfortunately also not possible. And the impossibility holds under some standard computational assumption, which we call learning with errors, or LWE. I'm not going to go into what that assumption means. So remember that we have these two types of circuits, C and Z. And if we want to use the same kind of proof as in the classical case, but now assuming that their obfuscation can be a quantum state, well, it doesn't go through for two reasons. We had this homomorphic evaluation step where we assumed that their obfuscation was a circuit, but now it can be a quantum state. So what does that mean? How do we homomorphically evaluate there? And the second point, which is arguably more important or harder to get over, is one of reusability. So in our classical proof, we have this obfuscation D, which we ran several times. We ran it to get an encryption of alpha, and then to evaluate this point function, this first line, and then to do a homomorphic evaluation, etc. And this may not be possible if our obfuscation is a quantum state, right? Maybe to evaluate your obfuscation, you need to measure something, or you need to do something else that destroys the state. So this reusability is really kind of a hard obstacle here. And in 2016, these Alagic and Pfefferman, they also tried to do this proof in the quantum setting, and they ran exactly into these two issues. So they were able to show that quantum obfuscation is impossible if you obfuscate into some reusable state, for example, a circuit or a quantum circuit or something. And if the circuits that you're obfuscating, the class of circuits that you're obfuscating is itself quantum. So kind of, they got some kind of impossibility result, but it was not really the one that we were looking for, interested in per se. So the quantum way out was still maybe possible. But in our paper, we fixed these issues with the impossibility proof. For the homomorphic evaluation, we homomorphically run the interpreter. So remember that if our obfuscation is not itself a circuit, then we have this extra algorithm, interpreter algorithm, together with it, which takes the obfuscation as an input and your X as an input, and then produces the circuit output. And to do this, we need quantum fully homomorphic encryption. In particular, we need quantum fully homomorphic encryption where the key is still classical. But since a few years, we have some excellent papers that actually fulfill this. And as for the reusability, well, there's two observations. So if the output is classical and deterministic, we can measure it, revert the interpreter, and then we get our original quantum state back, right? That's always with quantum circuits. If you already know that the output is going to be in a certain basis and it's going to be that value with high probability or with certainty, you can measure it and revert. So then you can reuse the state. But after a homomorphic evaluation, this is not the case, because the output may be a superposition of ciphertext. It might be always the ciphertext for the same value, but there might be different ciphertext for that value. So then we cannot do this measure and revert trick. So we have to do some extra work to make sure that this homomorphic evaluation step occurs last, instead of in the middle as it did in the classical proof. So zooming in on this circuit a bit, I'm going to make one change to it, and that's on the last line. It looks like a much bigger change than it seemed. I kept the functionality the same, but instead of saying if you evaluate this last line, we're going to evaluate this function, I'm saying if you evaluate this last line, so if you input 3 to your circuit, then you're just going to get a fixed classical obfuscation of this functionality in the brackets back. So this O sub CC, it's a classical obfuscator for compute and compare functions. And Harry already nicely plugged this question earlier. We actually know of a classical obfuscator for compute and compare function that is secure as long as this beta value is sufficiently random. So that's the only change I made. Instead of putting the evaluation directly into the circuit, I'm going to put a static fixed obfuscation. And what that does is the fact that now we can do this line, this last line, instead of doing it last, we can do it earlier on. So now your obfuscation is a quantum state, is D. It's not a circuit anymore with a quantum state, but we're going to do roughly the same thing. So first we're going to run the second line, or we're going to run the interpreter on the second line to fetch this encryption of alpha. Next, instead of doing the homomorphic encryption now, we're going to fetch this last line. So we're going to fetch this obfuscation of this functionality. Then we're going to run the homomorphic evaluation to turn our encryption of alpha into an encryption of beta or of 0, depending on which circuit type we have. And finally, we're going to run this last line, which we retrieved already in the second line, to get 1 if we had an encryption of beta or 0 otherwise. So 1 if we had a C circuit, or Z if we had or 0 if we had a Z circuit. And on the high level, nothing really changed about this adversarial program except that this homomorphic evaluation step is now the last line where we really use this D object, and potentially we destroy it now. But that's okay, because this last step, we don't need the D object anymore because we already retrieved it in step 2. So that's the only function of this O sub CC, is to make sure that even though we want the functionality only at the very end, we can already retrieve something that holds this functionality during earlier on. Okay, as a final slide about this impossibility proof, I'm going to give a little bit of a side note. If you're already thinking, oh, this was quite enough, then you can wait until you see a colorful table appear on the slide and you can zone out for a few minutes. Otherwise, I will tell you about this one single problem. I kind of glossed over it earlier, but our circuit returns a public key. And the size of the circuit grows, of course, with the length of the public key, right? If your public key becomes longer, then your circuit description or whatever grows. But the length of this public key grows with the depth of the evaluation, this homomorphic evaluation that we want to do. And the depth of the homomorphic evaluation grows with the size of the circuit. So we're kind of in a loop there, because then the size of the circuit grows with the length of the public key, etc. So this is slightly problematic. This was already a problem in the classical or in the version of the classical proof that I presented, not in the original paper, but where we took this homomorphic encryption inside the paper or inside the circuit. So one solution that's kind of a quick fix is to add an extra assumption, which is called a circular security assumption, which essentially will give you the a property that this public key size doesn't grow with the depth of your evaluation. So you're breaking this loop by assuming this, but we didn't want to assume this. So I'm going to scratch that with a nice animation. And actually what we do in our paper, and I'm not going to go into the details, is we defined a notion of decomposable public key. So instead of returning, I removed the encryption of alpha here for simplicity, but I guess it should still be there. And so instead of returning the full public key at once, you can return, or you can request like blocks of the public key, PKI. So you input an I into your circuit and you get a single block. So, and those blocks should be able to be generated efficiently, and their size is kind of independent of this evaluation depth. And to achieve this efficient generation, we use a pseudo-random function. And of course, we want the property that the public key can be reassembled from the blocks. And on the other side, the individual blocks don't reveal any additional information. So formally, we say that the distribution on the blocks can be simulated if you just have the public key. And many natural homomorphic encryption schemes that are built with bootstrapping, they already sort of naturally have this structure that they have these several public keys that are independently generated, or partially independently generated. But we also show that for any homomorphic encryptions or any encryption scheme, you can have this decomposability of the key. And we show this through some kind of garbled circuit construction.
Can I ask another question?
Yeah, sure.
And as a sort of this, you have this classical obfuscation in step 3 of your circuit. Don't you need that to be quantum obfuscation to go through?
Well, if it would be a quantum obfuscation, so that's this one, right? This last line here. If this would be a quantum obfuscation, then your circuits see
that it was classical obfuscatable.
Sorry, you
used the result that it was classically obfuscatable.
Yes. And
but
if
but
this
it
would be a quantum oh, sorry, go ahead.
But it may not be obfuscatable for a quantum computation.
What do you mean it may not be obfuscatable for a quantum computation?
Well, well, if I understood correctly, this is a result that says that if you have these compare functions, then you can obfuscate them.
Yeah. So there exists a classical object or circuit that is an obfuscation of this circuit family.
But maybe a quantum computer can see the difference.
Yeah. So this security of their obfuscation, it relies on some adversary not being able to tell the difference, and that itself relies on the learning with errors assumption, and that's a quantum secure assumption. And I mean, you have to go a little bit into how they actually reduce to that assumption, but it's also a quantum safe reduction. So that means that this obfuscation is also quantumly secure.
Okay, that wasn't mine. Good.
Yeah, it's an important detail, but yeah, it's okay. We thought about it. Okay, so that was everything I wanted to say about this decomposable public key. And I also now am kind of finished with the quantum impossibility result. So essentially the proof structure is the same, but because we're now dealing with quantum information, we have to be a little bit more careful about this reusability of the key, and also about the fact that we wanted to homomorphically evaluate something that's now not a circuit anymore, but a quantum state. But in spirit, the proof structure remains the same. Let me now compare to some earlier impossibility results. So this is the point where you can wake up again if you got lost about this decomposable key stuff. I mentioned both of these works earlier already before. So this 2001 was the original classical impossibility result, and the 2016 work was the first attempt to port this into the quantum setting. So the unobfuscatable circuit class, well, in the classical impossibility result, that was the class of all classical polynomial size functions, and in particular it was this like a very specific combination of these three options. In the 2016 result, the unobfuscatable circuit class was the class of all quantum circuits, and that's a slightly weaker result, right? Because it's a bigger class, so it should be harder to obfuscate. And then in our work, we kind of go back to saying, okay, impossibility of obfuscating classical circuits. And the thing into which we obfuscate, well, in the classical result, of course, they obfuscated into classical circuits, but you can quite easily extend this into general classical objects or strings. In the 2016 results, they generalized this slightly into what called reusable quantum states, so quantum states which you can use multiple times to evaluate the obfuscation. For example, a circuit, but they left open the possibility of other reusable quantum states. In our work, we strengthened this impossibility into saying, well, whatever your form your obfuscation takes on, whether it be quantum or classical, it's just not possible. And on the kind of downside of this, we need slightly stronger assumptions. So I already mentioned that the classical result, they assume that one-way functions exist, and in the 2016 setting, well, they still had the same assumption, but of course those one-way functions should be quantum secure in their setting. And in our work, we require that a variant of the learning with errors problem is hard. And we require that because we want to have this quantum fully homomorphic encryption there, which requires this assumption. And we needed this obfuscation of this classical compute and compare function. So this last step that Harry just asked about, and that also requires this learning with errors assumption. So to achieve our impossibility result, we need stronger assumptions, but these are still fairly standard assumptions in quantum or post-quantum cryptography. If I have some time left, I want to briefly mention some concurrent work on secure software leasing, which, well, it was put on the archive, I think 2 days before our paper. And it was really interesting to see how they really just had the same ideas where we thought we were being very clever in overcoming some of these hurdles. They used the same techniques. But the problem that they were working on was slightly different. So they were working on copy protection, and copy protection means that you have some function f and you have a quantum state that computes that function. So that really sounds like the obfuscation. But now the goal is that you can use the quantum state to compute the function, but you cannot copy it into two objects that would both compute the function. That's what quantum copy protection means. And they showed that this is actually impossible, and thereby they answered an open question posed by Aronson in 2009, I think. And they showed this via impossibility of an even weaker property. So even that weaker property is impossible, and then copy protection is impossible. And they also observed that this implies impossibility of quantum obfuscation. And their proof is very similar to ours. So they use the same circuit that I just presented to you, except for this last line where the compute and compare function, oh, it should be this one. We've just returned a 1 here, and they return some more rich information. And the reason for that is that their goal is slightly harder. We just wanted to construct a circuit class where an adversary can tell the difference between one circuit or the other. And what they want to do for this copy protection is they want to construct an adversary that can retrieve enough information about the circuit to actually construct the functionality and construct a copy from it. So that's a harder task, and they achieve it by sort of inserting some secret key information here. It's not exactly the secret key, but in spirit it is. They do require a circular security assumption for their result, which we managed to get rid of, but we think that the same techniques that we used would also be applicable to their work. And then to end this talk, there are some directions for future work. So we think that it might be possible to get rid of this stronger assumption that we need for our result. To do that, you would have to find an alternative for this quantum homomorphic encryption and for the compute and compare obfuscation. which is not trivial, but there are some directions in which it might be possible. But maybe to leave you on a sort of happier note with some possibilities. So weaker notions of quantum obfuscation may still be possible. So I only talked about this definition with the simulator and really learning nothing, but there are other notions of obfuscation which are still interesting for cryptography, which might still be possible, both classically or maybe even for quantum circuits. And this is one that Harry already kind of hinted at. Maybe we can actually achieve this strong definition of virtual black box obfuscation for smaller circuit classes, but circuit classes that are still interesting. And also completely unknown is whether you can obfuscate bigger classes if you allow quantum obfuscation rather than just classical obfuscation. We don't know of a separation between those two, but we also don't know that there are equivalent. And that's all I wanted to say. So thank you for your attention.